Hello friends, welcome to GreedyPie. I am Arham Doshi and let's get started. In this video, we will be discussing about two things. First is first is the comparison between different sorting algorithms, and another thing is the question, that is selecting the kth smallest element from an array. Okay. So when discussing about the comparison between sorting algorithm, what are the fields on the basis of which we can compare them? First field is obviously time complexity. But in this also we have three things, that is the best case time complexity, average case time complexity, and worst case time complexity. Another thing is space complexity, and uh, another name for space complexity is whether it is in place or not. So if we can run an algorithm such that it will only take constant extra space, that is no extra space other than what it has, it then we will call this an in place algorithm. So it is in place and it is not. Okay. And another thing is we can compare on the basis of whether an algorithm is stable or not. Stability is basically if uh, if two elements there are such I and j is such that uh, the value of arr I is equal to arr j, then after sorting we should get them in the same order. Okay, so let's take an example. Let's say we have an array something like this. After sorting we'll get array like this, but in this case we cannot find whether it is stable or not, because we don't know this two is like this two or like this two, and we don't know like this one is this one or not. But when we talk about some real life scenarios, we will be sorting just the key of an object. Okay, and let's say this is an object 1 and let's say this is an object 2, and this is just a key representing both. And after sorting, if we find that this element is denoting object 1, but before sorting it was before this particular object, so in this case we will come to know that elements having equal values have not maintained order, and in this case we can say that algorithm is not stable. So another important matrix while comparing the algorithm is swaps. Swaps is basically number of times we swap the elements of the array. So why? So now why this is important? Let's say we want to sort an array and it is of size n, and the array is of like strings, and each string of is of like size m. So if we want to swap two elements, what we need to do is we need to like put, like let's say we want to swap two elements. First we need to put value of one element in like temporary variable, and then we have to put the value of another variable in the first variable, and then we will have to put the value of temporary variable into the second variable. So in this case the time complexity of swapping an element is like of m. Okay, so if we want to find the complexity of an algorithm, and if we are using an n log n algorithm, then the time complexity would be n log n plus the complex plus the number of swaps into m. So in this case, this is, if n is small, so this is not the dominant factor here, and this is the dominant factor. So in this case we will be using algorithm which is reducing the number of swaps. Okay, so now let's compare all the algorithm. So we will first look at the optimized bubble sort. In optimized bubble sort, what we are doing is we will use bubble sort, but if we get to know that we can no further sort this array in one pass of the bubble sort, there is no element being swapped, then we will stop there. So best case time complexity of bubble sort is of n. So if we pass the already sorted array, then after one iteration it will stop. The average case complexity of bubble sort is n square. In the worst case is also n square. So what is benefit of bubble sort is the code is very simple. That's the only benefit. Okay. So the memory it will require is constant, because we are not using making any extra array or something. So whether it is in place or not, so if memory is constant, it is in place. Whether it is stable or not, yeah, it is stable. And how many swaps it would require? In worst case we will require n square swaps. Okay. In selection sort, we are selecting the minimum element and like then replacing it with the current index. So best case time complexity is like for every, so whether or not an array is sorted, we will like go through all the elements in one iteration and then select the best, and we will do it for n times. So the best time complexity is also n square, average and worst is also n square, and we are here using just we are and in this also we are not using any extra memory, so the memory is also of 1. It is like whether it is in place, yes. Now when we are talking about the stability, we cannot say, because so if we are having more than one element, that is minimum, like let's say uh, this is the case here. If we are choosing one, then for the first iteration if we are choosing this one, then it is like stable, but if we are choosing this one, so it is not stable. So in this case it depends on the implementation, we can't say. But the best thing is we will be swapping only n times, so the number of swaps in this algorithm is n. Okay. When we are discussing about insertion sort, we will select an element and then try to insert it in a already sorted manner. Okay. So best case time complexity is we will first find so we will be having the array in already sorted order, so we'll have to do no swaps, and the best case time complexity would be like O of n. The average case would be like n square, and the worst case would be like also n square. The it we are also not using any extra memory, so the memory is of order 1 and it is also in place, and it is a stable algorithm, uh, and number of swaps in the worst case would be n square swaps in the reverse sorted array. While discussing about the merge sort, the best, worst and average all three are of n log n, because in each iteration we will be making like n log n recursive call, and for each recursive call we will always be doing of n operation, and the memory required here would be for uh, each recursive call we will make an arbitrary array, and in which we will try to merge the list. So the memory required would be like log n plus n, and log n here is not the dominant factor, so the memory requirement would be of n. And it is in place, yes it is in place. Whether it is stable or not, yes it is stable, and the maximum swaps we will be doing is n log n. Now discussing about randomized quicksort. So in randomized quicksort, what we will do is we will choose a random pivot and we will try to partition based on that. So the best case complexity would be like of n log n. uh, the average case complexity would be also of n log n, and the worst case complexity would be n square, because if we are given already there is a very slight probability that we will choose already the maximum or already the minimum element, and in which we will decrease the size of the partition by just one at after each recursive call. So the complexity here would be n square, and memory used time space complexity would be log n, that is the space occupied by the recursion stack. Okay. And it is an in place, but because it is randomized, we can say that it is definitely not the most stable algorithm. Okay. and number of swaps here required would be of that of maximum uh, worst complexity, and it would be like n square swaps. Now let us discuss about counting sort. In counting sort, we are just iterating over all the elements, putting them into a bucket array, and then we are printing them. So the best, worst, and average complexity, all three would be equal to n plus m, where n is the number of array elements in an array, and m is the maximum element in that array. And the memory location required would be like of m, because we will be making an extra array of size m. Whether it will sort in an in place or not, so it depends on the implementation. So the merge sort and randomized quick sort is not having space complexity as one, so they both are not in place, sorry. And in this case also we are making an array of size m, so this is also not in place. Whether it is stable or not, we don't know, because it depends on the implementation. And regarding swap, there are no swaps, so we cannot say anything about it. Okay, yeah, that was it. Now let's move on to the question. So the question is, find the kth smallest element in an unsorted array. So you are been given an array. Let's say the array is something like this: 6, 10, 5, 1 and 3, and we want to find the element that is the second smallest element. Okay, so after sorting the array, we will get an array 1, 3, 5, 6, 10, and the second smallest element would be this. Okay, so how can you do it? The first and most simple approach would be sorting the array, and it will require like n log n space, and after that we can just print the element at k minus 1th index. Okay, so now how can we try to optimize it? Can we do better than n log n? The answer is yes. We can like we can solve this question in of n time complexity using a algorithm called quick select. It is a modification of quick sort. In quick sort, what we were doing is we were selecting a pivot, and then after we were doing a partition subroutine, and after the partition subroutine we were getting the actual position of the pivot in that array. Like after partitioning we will get to know that this is the actual position of this pivot element, and all the elements before the pivots were less than p, and all the elements after the pivot were greater than p. So how can we use this partition subrouting to solve the problem? So after doing partition we know the value of pivot element. Let's say the index of pivot is x. So after in the sorted array, all the elements that are like greater than p here have will also have index greater than x, like will also have index greater than x in an sorted array. 2, 3, 10, 5, 6. Okay, so we will take an pivot that is 6. We will try to partition. We will get the partition like this: 2, 3, 10, 6 and 5. Now we know that 6 is at its. Now let us understand this with an example. Okay, so let's say we have an array 3, 2, 5, 10 and 6, and we want to find the element that will be at index 1, that is second smallest element after being sorted. So let's take the pivot randomly. Let's take it 6. So after applying a partition subrouting, we'll get results like this: 3, 2, 5, 6 and 10, and we know that 6 will remain at this index even if the array is sorted. Okay, and all the elements before 6 will have the index less than 3, and all the elements greater than this will have index greater than 3. Okay, so after doing one partition routing, we will be getting the index of the partitioned element, and we will see whether our index we want to find, let's say the index is like I. If it is greater, after doing a partition subrouting, we'll get the index of the partitioned element, let's say it j, and let's say we want to find the element at index I. So if the element we want to find is equal to j, if I is equal to j, then we know that we have already got our answer, and we can just return the pivot element, that is 6. If the index that we want to find is like less than j, we will be looking only at this half of an array, and by doing this we can completely neglect whatever it is the other side. And if we want if the index we want to find is greater than j, we will be looking at this side of an array, and in that case we will be completely neglecting this part. So at each step we will be like approximately reducing the size of the array by half. And if we sum everything this, and in first partition phase we will be looking at the array with n elements. The complexity of the first partition phase is of n. The complexity of second partition phase would be of n by 2, and similarly it will go till 1. So uh, if we add up all this, the total complexity would come to be of 2n. So we can reduce the exclude the constant, and the complexity would be of n. So now let's look at the code. We will first try to implement quicksort, and then we will try to modify it into quick select algorithm. In this, what we are doing is we are initializing a random seed value, and we are just taking the input to the vector. We are calling quicksort, and we are just printing the array after quicksort. In quicksort, we are having an index L or R, L to R, that will tell us the sub array which we need to sort of the vector v. And in quick select, first we'll check the base case. Base case would be like if the sub array is of size 0 or 1, then we can just say that it is sorted, and we'll go back. So if L is greater than or equal to R, then we will say that it is already sorted. Otherwise we will select some random pivot from L to R. We can just swap the pivot with the last element, and then call the partition subrouting. Okay, so we will be first getting the size of the server, and then we'll be getting the index of the we will be randomly generating the index of the pivot. Wait a minute, this is pivot, so it would be like this. So random percentage sz will give us a random number from 0 to size -1, and we can just add it to L, and that will give us a random value of pivot. We'll swap the pivot with the last element. We'll just send the pivot to the last element, and we can run the partition subrouting in this, and we will be getting index of the pivot element after bin partition. And this index would be such index that if we sort the array, the pivot element would be at that index. Okay, in partition subrouting we will be maintaining an invariant j, and after being called a partition subrouting, all the elements from index L to J would be less than pivot element, and all the element from J to R would be greater than or equal to pivot element. Okay, so we will just iterate through all and we'll try to maintain this invariant. What we can do is, if we will find some element that is that is less than pivot, we will add it to the uh, invariant, and we can just increase the size of the invariant. So if like this is less than pivot, we can add it to our invariant array, and at last we will swap we will put the pivot element at its index, that is at index j, and we can just return its value. So now we got the position of the index of the pivot element. What we can do is, we can now run quick sort from L to part minus 1, and we can now run quick sort from part plus 1 to R. That is, the we know the index of pivot element. We will, all the elements to the left of it will be less than pivot, and all the element to the right of it will be greater than pivot, and we can run recursively quick sort on it. And what it will do is, it will basically output the sorted array. So now now coming to our question of getting the kth smallest array, we will just modify this a bit. We can like take the input as k. We'll just give the input as, we will just give the input as k minus 1, because the kth smallest element would be of index k minus 1, and here we'll keep it as index. And after getting the index of partition element, uh, if the k is equal to the index, then we can say that we have got the element. If k is less than that, we will have to query the array that is in the left of the part, and otherwise we will query the array that is like right of the part. So if, then we can just return this value, else if part return xor v comma l comma minus 1 comma index. Okay, and if it is not, if the index is not less than part, then the index would be greater than part. Then we will query only the right half of the, so let's see if it is works, if it works or not. So after this you can see that it is giving our answer. Yeah.